Hello, my name is Roy Simpson, and I'm a professor of mathematics at Cosine College in Sacramento, California. This is another proof in my series on proofs in differential calculus. And in this proof, or this video, I'm going to go ahead and prove that the derivative of the cosine inverse of x with respect to x is equal to a negative 1 over the square root of 1 minus x squared. There are a few things that I want to establish prior to beginning this proof, and a couple things I need to say as well. First of all, in your calculus class, your differential calculus class, you may find that you are learning a lot of different derivatives, and it turns out that these derivatives, specifically the derivatives on the left-hand side here, occur almost all the time in integral calculus. So you'll need to know at least the left-hand side by heart pretty quickly because they end up being super important. In fact, the left or right-hand column is also incredibly important, but I find that actually the tan inverse derivative is incredibly important in calculus 2 or integral calculus, whatever you want to call it. The other piece of information I need to talk about is what our prerequisite knowledge should be, and a bit of a warning. So you should know about trigonometric inverses, but I'm going to make a little warning about the cosecant inverse, the secant inverse, the cotangent inverse, because they're defined somewhat differently for calculus than they were for trigonometry. And also, your prerequisite knowledge, you should be pretty strong with implicit differentiation, or at least be able to handle yourself with implicit differentiation. Now let's go ahead and talk about trigonometric inverses really quickly, because it is going to be a tripping point for people. So we'll first start by recalling that theta equals sine inverse of y implies that y is equal to sine of theta. And a lot of people are pretty okay with this, but remember there's a restriction on theta here for it to maintain itself, well, basically for the sine inverse to be a function. We have to restrict theta to be between, in radians, negative pi over 2 to positive pi over 2. And if you don't believe me, I've tried to do this video a few times without being too reviewy, but it just didn't work out. So instead, I'm just going to say that you should probably be already pretty strong with trig. I'm just going to tell you right now that these are the ranges of the sine inverse, and then we'll do the cosine inverse and whatnot as well. So speaking of cosine, theta is equal to cosine inverse of y implies that y is equal to cosine of theta. So that's what theta will be for the cosine inverse. The tangent inverse is the same argument. And if you draw that out, you will see that your angles have to be restricted between negative pi over 2 and positive pi over 2. And that's not including the endpoints because of vertical asymptotes. Now, this is all fine, and you recall this from trigonometry. However, in trigonometry, you had different restrictions for the cosecant, the secant, and the cotangent inverses than you will in calculus. So I will write down the restrictions for the inverses of those functions for calculus here, so that we know what to do. So if theta is equal to cosecant inverse of y, then y is equal to cosecant of theta, where theta is either in quadrant 1. All of these, by the way, all the inverse trig functions return at least into quadrant 1, or theta is in quadrant 3 between pi and 3 pi over 2. Okay, so that's I'll illustrate that in a moment. That's the only one I will illustrate. Okay, so theta is equal to secant inverse of y means that y is the secant of theta, and theta is either in quadrant 1. And remember, you have some not inclusions here, mainly because of vertical asymptotes, or if your y value is negative, that your angle is between pi and 3 pi over 2, which is quadrant 3. And finally, for the cotangent inverse. And this is the only one of the invertible functions for these cosecants, secants, or cotangents that actually makes sense. Theta is equal to cotangent inverse of y implies that y is the cotangent of theta, where theta is either in quadrants 1 or quadrants 2, and it's between 0 and pi. So let me illustrate the reason for these choices, just for one of them, just for the cosecant. So you should probably recall that to graph the cosecant, you go ahead and graph the sine curve first. And then you can, wherever the sine crosses 0, you have vertical asymptotes for the cosecant. I'll draw those in. And I'll go ahead and draw a green cosecant curve. And, that pattern repeats on and on and on. Okay, so now we need to restrict the domain of this cosecant curve so that the inverse is a function. So that means that we need to restrict our inputs, or in other words, we want to erase enough of the green curve so that we still capture all the outputs. In other words, all the stuff that goes to positive infinity all the way down to 1, and then all the stuff that starts at -1 and falls all the way to negative infinity. And we have a bunch of choices for this. We can either, and I'll highlight first, we can either capture all this stuff, so keep this and keep this. And those are perfectly fine choices, honestly. In your calculus class, those aren't the choices that are made, but those are actually perfectly fine choices. So if you want your angles to go for your restricted domain to go from a negative pi over 2 all the way up to 0, and then start again at pi over 2 and go all the way up to pi, that's perfectly fine. Oh, this is supposed to be a pi right here. That's perfectly fine. But that's not, again, how your calculus class does it. So we're going to undo all that, and we'll go ahead and show you what your calculus class does. Your calculus class ends up restricting the domain this way. Well, I should say possibly your calculus class. I know that all textbooks should restrict the domain to go at least into the first quadrant. In other words, from 0 to pi over 2. So that's very important. You'll notice all inverse functions restrict to go from 0 to pi over 2, and that was mentioned in our previous page here. Let me see if I can find it. Yeah, right there. That in this page, you notice all of these angles at least exist between 0 and pi over 2. 0 and pi over 2, 0 and pi over 2 is in this one. 0 and pi over 2, 0 and pi over 2, 0 and pi over 2. So they all have 0 and pi over 2. That is part of their domain. However, if we continued to go from pi over 2 to pi here, all we would get is a repetition of outputs. That's not what we want, because that'll make the inverse non-invertible, or not a function, sorry. So what we want to do is we want to skip over the next chunk and then pick up at pi and continue on to 3 pi over 2. So let's go ahead and highlight that. So we want to keep all this other stuff here, but not anything otherwise. So I'm going to go ahead and erase everything else. We see that we have all the possible outputs for the cosecant. Everything from negative infinity all the way up to this height is a -1. And then everything starting at 1 and going to positive infinity. And we have angles, just enough angles to get us those values, but nothing overly much, right? We don't repeat any outputs at all. So this is the restriction. This is why the restriction for the cosecant inverse is for angles, is between 0 and pi over 2 and pi and 3 pi over 2. So if you look at the cosecant inverse, 0 to pi over 2 and pi to 3 pi over 2. Notice that we don't include 0 and we don't include pi. Reason why? Those are vertical asymptotes. Okay, so you could do the same argument to figure out why they have these other restrictions here. But the fact is, the inverse functions for the cosecant, secant, and cotangent always have these weird oddball ones for calculus, these oddball spaces, except for the cotangent. Cotangent actually makes sense. But it's going to be important for any type of proof you're going to do for the derivative of these. Okay? So let's go back into this, and in fact, maybe I will... maybe I'll go ahead and prove another one of these as well. So let's go ahead and do both the inverse cosine derivative and the inverse cosecant derivative. So the inverse cosine, they're going to involve similar arguments, but I think it's important because of the oddball structure of the inverse cosecants to do one of those as well. The rest of these are fair game for exams. Your instructor should actually give you one of these on an exam so that you can argue logically, and you also have to recall all the ranges, the limited ranges. Okay, so we know we want to take the derivative with respect to x of the cosine inverse of x. We're going to go ahead and start with let y equal the cosine inverse of x. Because the fact is, I can't just start and say, let me take the derivative of the cosine inverse of x. I have no idea what the derivative is yet. I'm not supposed to know. But at least if I say this, then we could say that x must equal the cosine of y. And there's some slight restrictions on x, so maybe I should mention that, where I'll mention domain restrictions here. Our angle y has to exist between 0 and pi. Okay, great. Let's go ahead and maybe take the derivative of this, because I happen to know the derivative of the cosine. So we'll go ahead and say therefore, and we'll do implicit differentiation, since that was part of the required pieces of information for this proof. So I'll write out the derivative separately. We have the derivative with respect to x of x itself equals the derivative with respect to x of the cosine of y. Notice that second, or in other words, our right-hand side, is actually a function of y. And y is a function of x. So that's going to be a chain rule there. On the left-hand side, the derivative of x with respect to x is just 1. On the right-hand side, well, let's start on the outer function here. So the derivative of a cosine of junk is just going to be the negative sine of that junk. And then we'll have to hop inside the function to take the derivative of the inside. So the derivative of that y is what we have remaining. So times dy dx. And remember, what we're trying to do is find out what is a derivative with respect to x of y, because that's what the cosine inverse of x is. So I'm going to solve for dy dx here. This implies dy dx is equal to negative 1 over the sine of y. Now, I don't want to leave my answer in terms of sine of y. I want my answers in terms of x. So this is where I'm going to draw a very quick triangle. I use a lot of right triangle trigonometry in my mathematics. And we happen to know that x is equal to the cosine of y. So y is our angle. And I'm going to use this. I know that it's technically not our angle. This is actually a reference angle. But if you know quite a bit about trig at this point, which you should be okay with this. We know that the cosine of y is adjacent over hypotenuse. So the adjacent should be x. The hypotenuse should be 1. And we can find, using Pythagorean theorem, the opposite is just going to be the square root of 1 minus x squared. And now we also should probably mention pretty quickly here that, let me draw a set of axes, just a really fast set here, that our angle y is either going to terminate in quadrant 1 or it's going to terminate into quadrant 2. So this angle is either we have a quadrant 1 angle or quadrant 2 angle. That's what we said right here. So this means that our outputs, I don't want to say our y values because it's getting a little confusing that way. Our vertical values, our opposites, I guess you could say, are always going to be positive. So what I'm drawing right here, let me just highlight it so you can see that. Because we're in quadrants 1 and 2, you should agree that this little highlighted region, that highlighted line, which happens to be the same as this highlighted line, should be positive. Okay? So let's go back to the proof. We know therefore that the derivative, so let me write this the other way around. I'll say the derivative with respect to x of y, which happens to be, by the way, derivative with respect to x of the cosine inverse of x, is equal to a negative 1 over, and let's see, the sine of y here is going to be opposite over hypotenuse, square root of 1 minus x squared over 1, which is just a pretty little square root of 1 minus x squared. I use the fact that that highlighted portion, the vertical portion there, is positive to say that, well, guess what? I don't need to put a negative sign here. I don't need to guess. I know that this is positive. So it's a negative 1 over the square root, positive square root of 1 minus x squared, which, by the way, is exactly what we wanted to prove. So that proof is done. QED. So now let's go ahead and just quickly do the second proof in blue there, the cosecant inverse of x. I start exactly the same. I just say, well, you know what? I don't know the derivative of that, so I'm going to go ahead and let y equal the cosecant inverse of x. Then we happen to know that x should equal the cosecant of y. And we have to make a little restriction, a little note about what y exists between. So we'll say that y is an element of the following intervals. So that was from our earlier discussion, this one right here, where we developed that stuff right there, and it was also developed right here. So I'm just using that in our proof here, and now I will go ahead and say therefore, just like I did in my previous proof. Therefore, we're going to go ahead and say the derivative with respect to x of the left-hand side of that should equal the derivative with respect to x of the right-hand side of it. Again, I'm not tackling the cosecant inverse because I don't know the derivative of the cosecant inverse. The derivative of the left-hand side is just 1. And the derivative of the right-hand side is, again, another chain rule. So we'll go ahead and say, all right, we have the derivative of the outer function, which is the cosecant. You should know that derivative already. That derivative is going to be the negative cosecant of whatever was on the inside of it times the cotangent of whatever was on the inside of it. And then we'll have to hop inside that function and take the derivative of what was on the inside, which is y. So times the derivative of y with respect to x. And again, that's using the chain rule there. Okay, so let's go ahead and solve for dy dx. And I'm going to change sides here as well. So this implies that dy over dx is equal to a negative 1 over the cosecant of y times the cotangent of y. And I'll say this is equal to, but I know I'm going to have to draw a triangle here, so I'll draw my triangle. We happen to know the angle itself we're calling y, and again, this is kind of y hat, honestly, it's a reference angle. And we know the cosecant of y is x over 1. Cosecant is hypotenuse over opposite, so hypotenuse is x, opposite is 1, and we can use a little bit of Pythagorean theorem here to find out that this will equal the square root of x squared minus 1. Okay, so let's go ahead and go back into this. Also, I should probably note, actually, now that I'm thinking about it, let me draw out this. We happen to know that that our angle y here is either in quadrant 1 or it lands in quadrant 3. That's important to note. So it's either in quadrant 1 or quadrant 3, and that's just from these two restrictions. It's incredibly important to note. All right. So we find this out. That's negative 1 over, well, the cosecant of y is going to be, well, we already know what it is. We said cosecant of y is just x, so we know that's x. The cotangent, on the other hand, is not opposite over adjacent, but the reverse of that, adjacent over opposite. So that's going to be square root of x squared minus 1. Now, notice where that is in this triangle. It is the horizontal side, so let me highlight that. That is the horizontal side. Okay. And we have this vertical side that it's going over. So it's horizontal over vertical, right? Well, if you look here, horizontal over vertical, it's positive over positive, it's positive, right? In quadrant 3, horizontal over vertical is a negative horizontal over a negative vertical, it's still positive. So no matter what, this ratio of root x squared minus 1 over 1 will always be positive. So I don't have to worry about a plus or minus sign here. All I have to do is just write it down. I know it's going to be positive, and we're done. Okay, so this tells me that the derivative of, with respect to x, of the cosecant inverse of x is just equal to a negative 1 over x times the square root of x squared minus 1. Honestly, during an examination, you could easily knock out this proof in probably about, a minute, maybe 2. But I spent quite a bit of time on it just so that we can develop kind of the theory behind it a little bit more. I wasn't super rigorous with it, but rigorous enough that it should give you a good explanation.